Hello, everybody. This is Professor Ma, and this is sections on antiderivatives. So, for the last few months, we've been taking derivatives and all kind of application for derivatives. Now, we're going to do the entire things backward, and then find out what are the applications for the algebra for doing all these things going backward. What are we calculating? The antiderivatives. So let's start out with the first theorems, which is kind of obvious. Okay, they came out of mean value theorems that we just went through. That is, if I know the derivative of a function is zero for all the number x, okay, in an interval, then the function must be a constant function. Derivative of constant function is zero. Okay. On the other hand, and the derivative is zero, then the entire function must be a constant functions. The proof basically is restatements of the mean value theorems, and I'll let you read it. Basically, you're going to find that somewhere in the middle, the derivative is zero because uh, because by the mean value theorems, and then hence the numerator has to be zero, so f of x has to be a constant. So what's the point about the theorem? The point about the theorem is that if I were to ask the questions, what formulas derivative zero, there isn't one single formula. It could be any constant. So the antiderivative of zero is the class or the set of all constant functions. And the antiderivative is a whole bunch of functions. It carries over to all antiderivatives. Okay. In other words, if I take, we say a capital F of x antiderivative of little f of x. If I take the derivative of the capital one, big one, the little ones. Okay, and we write it backwards as the this. Okay, so this gives the meanings df. Well, this means that. Okay, and we call this capital F the indefinite interval. Okay, the word V is actually misleading because there's no a single one. There could be there could be a whole bunch of them, and they all are different by a constant. In other words, f of x plus 3 pi is another antiderivative of f of little f of x. And so any capital F plus a constant k, because the derivative of k is zero. So the derivative of capital F will be little f. Okay, so again, we get a whole class of functions. Derivative of a function is a single function. You take a derivative, but when you go back to antiderivative, you get a whole slew of functions. And you will see shortly on the picture what they meant. And two antiderivative of the same formulas, okay, must be different by a constant. Okay, we just went through that. Let's take a look at some of the basic integration rules. These are rules going backward from derivatives. So it's from the derivative can be the sum and the difference derivative is derivatives of the sums and difference. I can interchange the order of operation. So antiderivative, this is true also. Okay, again, we will say we can, before we say we can take derivative term by term. And here we say we can integrate term by term. Okay. And secondly, constant can be pulled out when I take derivatives. So when I integrate it, I can put it backward the same way. Okay. So the constant for integration can be pulled out. Notice it has to be a number. I cannot pull out anything with x in it. If I'm taking derivative, antiderivative with respect to x, like x times cosine x, if I want to know what antiderivative of this is, I cannot just simply say, oh, let me take the x out and this is going to be x times antiderivative of whatever. This you cannot do that. But if this is a number 5, oh yeah, that's okay. Okay, make sure you know this. We call this again polar constant multiple. Then we have a list of simple integration formulas, antiderivative of formulas. And these came from antiderivative of the derivative of simple formulas. So here they are. Okay. If I'm integrating a power function, when I take a derivative of a formula f5, I will get x to the 4. Okay. Notice the 4. So if I go backward, if I want to integrate x to the 4, take antiderivative, I will get something related to the x to the 5th. It must come from x to the 5th. But there's adjustment of a constant. So and the adjustment is this. Okay. So antiderivative x to p is x to the, you add 1 to the exponents, then multiply this or by 1 divided by p plus 1. So when you take the derivative, the exponents comes out, it will cancel with these terms. Okay, so that constant balance out the derivatives, give you precisely x to the p. And these are and also these are list of trig functions and the list of the for the antiderivative e to the x and antiderivative 1 over x give you the log x. Okay, so these are the basic list of taking antiderivative. Now, with the rules we had, what rules? And these rules over here that you can break it up, you can pull constants out, we can actually integrate these formulas. Okay, and the trick about integrations of formulas is first, you can see if you can break it up into term by term and do a term by term, if that's possible. Okay, here, okay, the 3 or 4 terms. Okay. I'm going to break it up into term by term. Constant multiple comes out. Okay, integrate term by term. And here there are actually 2 terms. Okay, break it up, set over x. And now I can integrate each individual components. Okay. And no quotient rule, no product rule. Okay. Very important. This is the difference between antiderivative and derivative. So that makes the antiderivative a lot harder. In other words, there's no single patterns ways to tackle antiderivative. And the derivative problems are the infinite varieties of them, and they involve all different techniques. But for this simple one, if we can break out into term by terms, and then we can do a term by term like this one, that's the first step we do. Okay, in approaching taking antiderivative. Then we'll put a plus k. Remember, okay, you have to have a constant there. Now, why is the constant there? Well, the antiderivative of 2x is x squared. Okay, and it's a class of formula, so you plus a constant there, and the picture for f of x equal to x squared is a parabola. So with different constants, have these parabolas, layered out on top of each other. And notice for each one of these parabola, if I choose an x over here, okay, and if I look at the different points on the parabola at the location, and they all have the same slope, f prime of, they all the same thing, they're parallel. That's why for all these derivatives, you will come out twice of x. That's why we couldn't, the antiderivative has a plus k, because just knowing the derivative is 2x is not enough to tell me which one. In fact, one type of problem that we're going to do is to recover this. Recover what? Recover which particular one we look for. We need more information about it. Okay, so here is a problem which we call try to find which particular ones that we are talking about by giving you extra information of a point. And this extra point, usually in mathematics, we call this initial condition. That is, we know a data point of the formula we're looking for, x equal to 3, y equal to 5, and we store over there. Then we get a whole bunch of formulas. Then we check which one has x equal to 3, y equal to 5. Okay, that condition we call initial condition. Okay, so here's examples, and particular one, since we need f of x equal to number, we have f of x equal to x squared plus k, right? And 1, 3 means f is 3, y is equal to 3, x equal to 1, and plus k. So the one that fit, k must be equal to 2. Hence, this one must be x squared plus k plus 2. Okay. And this we're going to phrase in terms of velocity and accelerations. Okay, so here's a problem that we know the second derivative, okay, or the acceleration in physics, okay, and it says what it is, and then with the conditions, I tell you what the first derivative and one is, and what the distant function itself is one. So these are the initial conditions, right? Two of them, because we're going to get two functions out of it. We're going to find the velocity. Okay, how do you find velocity? Integrate. Okay, how do you integrate that? Remember, if you can do it term by term, okay, there's no, again, there's no power. We cannot say, oh, let me just add this 1 to the power becomes 3 and do something with it. No. This only work for, power will only work for if you integrating t squared with respect to dt. Then yeah, this is t to the third divided by 3. This is okay. Okay, but nothing like t minus 1 minus some complicated formula in this one. Okay, so first, there's no fancy rule for this. And then the next is what? Do a term by term. How can I do a term by term? Multiply out into term by terms. Then I can do a term by term. Okay, and here comes the first initial condition, because I have now the velocity integral of the accelerations, and I know I have that what that function is, and now I'm going to plug in 1. Okay, because it told me once I should do 1/3. So I'm putting 1 for x, and that enables me to find out what k is. Okay. These, if you understand this, then you understand this type of problems. This type of problems is that something is given about, or you're looking for formulas, and they give you some like second derivative, first derivative. They tell you something about the formulas, and then you try to recover the formula. Okay. And then the method for recovering it, it doesn't quite give you the exactly which one it is. And at that juncture, you need a numerical number to plug in initial condition to get the specific formula. Okay. And one more time, this is called a general formula because I don't know what k is, but once you plug it in, you can find out the specific formulas with the initial conditions. So we'll do this again to find out what xt is. So I'm not going to explain this. Then plug in the initial condition for x1 to 1/2 to find out what the number k is. Then you finally get back to what xt is exactly. Okay. One thing I wish to point out that in terms of derivatives. Okay. That is, if polynomial has degree n, okay, then if you take derivative one more times that n, you're going to get 0. Okay, what do I mean by that? Look at the formula x cubed. Its first derivative is 3x squared. Its second derivative 6x squared or x cubed second derivative. Let me write that way. Double prime. It's going to be 6x. Okay. And x cubed third derivative. Okay, it's going to be 6. It will be a number. Okay. One more time. If a degree is 3, then you take derivative 3 times, it spits out a number. Which means what? Which means if you take it one more time, it's going to be 0. Okay. So if degree of p is n, then you do it one more times, n plus 1 derivatives, you're going to get 0 because the one before the nth derivative is a number. Okay. This is for any power of integer power. Which means what? Which means if I take derivative of two functions n times, they come out the same. So the nth derivative of capital F is the same as the derivative of capital G. You take the derivative many times, they're the same. What can you conclude about the original formula? Well, the original formula must be different by a polynomial with degree smaller than n. Hence, when you take derivative n times, that polynomial disappears. Hence, the derivative is the same. Okay. So, for instance, the derivative of e to the 2x and e to the 2x plus x cubed. Okay. If you do it 4 times, because it's x cubed, if you do 1, 2, 3, 4, 1, 2, 3, 4, you're going to get the same thing. That's what this theorem says. Okay. That's it. Okay, and do the homework, and bye-bye. Adios.